So a gas stream contains 90% mole percent. This is the mole fraction. This is the small x. So since it's a gas phase, we use y. So this is the small parameter. So a gas stream contains 90% nitrogen and 10%. Sorry, I write again x and 10% CO2. This is my y. So this is a gas stream that has CO2, and we want to separate this CO2. So is a strip absorption column that we are going to separate CO2. So we send CO2 from the bottom of the column. So bottom of the column, we have yn plus 1. This is my mole fraction. Is passed through an absorber in which pure. So we are using pure and cold water as a solvent. So the water is coming from top. At the top we have x. Okay, first of all is water, is a liquid phase, so we will use x. So which, since it's coming from top, at top we have x0, which is 0. The operation is assumed to be isothermal, isobaric, so at 10 atmosphere. This is an important parameter that we need to use. The liquid flow rate is 1.5 times the minimum liquid flow rate. So we need to find the minimum liquid flow rate, or L over G. So sometimes instead of vapor V, we use gas as well. So this is the same as V. So the L over G operating is 1.5 L over G minimum. So we have to find this minimum first times 1.5. That gives us the operating one. Determine the number of equilibrium stage to absorb 90% of CO2. So we have CO2 coming to the column with this mole fraction. 10% means 0.1. That has 10% CO2 and 90% nitrogen. And at the end, we want to separate 92% of my CO2. So if I have 0.1 at the beginning, I want to separate 92% of this. And at the end, I want to have only 8% of the initial value, which is this one, at the exit. Henry constant for CO2 in water is given this. So this is Henry constant is actually a constant that we use for equilibrium. Okay, Henry constant is for equilibrium, to plot the equilibrium line that you will see in the next slide. And it's saying that use a basic of 1 mole per hour of gas mixture. 1 mole per hour of gas mixture. Okay, so let's plot our let's show this information in a this is the Henry constant. Okay, we will use it for equilibrium line. Okay, equilibrium line is a line that relates x to y. So is a line that is a straight line that is y mx. M is a constant, is a Henry constant here, which is h. But look, this parameter doesn't have any unit, because here we have y, which is mole fraction, here we have x, which is mole fraction. So this shouldn't have any unit. So h, the Henry constant, is given in atmosphere per mole fraction. Mole fraction is not unit, it doesn't have any unit. So here we have Henry constant in atmosphere per mole fraction, and the pressure is also given 10 atmosphere. So if I divide my Henry constant by pressure, I can make this unitless number. It's like this is an atmosphere mole fraction divided by atmosphere gives me mole fraction, which is kind of unitless. So this is how we plot our equilibrium line, by using this equation. Y is equal to mx. M is Henry constant divided by pressure. Now Okay, so this, if I want to draw my information, this is what I have. I have a absorber column. I have an absorber column. I have my water, which is pure, coming from top. Okay, pure coming from top. Those are all lowercase x and y, lowercase, this one, not the capital case. Okay, lowercase x and y. So water is coming from top, which is pure, mole fraction 0. I have CO2 and nitrogen coming from down. I have 10% CO2 in my stream. This is the CO2, which is the solute, and 90% is nitrogen. And then I want to absorb 92% of the CO2. From this CO2 that I have at the beginning, I want to absorb 92% and have only 8% of the initial CO2 to leave at the top. Pressure is given 10 atmosphere, temperature 5 degrees C. And question is telling you that consider a basic for V, which is 1 mole per hour. So, and then you are asked to find the number of stages, total number of stages, by plotting method. So you need to do two things here. You need to find first operating, you have to plot the equilibrium line. You need such a plot. You need to plot your equilibrium line. So yeah, this is, you need to plot, let me plot it in the better way. So this is your equilibrium line. And this is your operating line. Equilibrium line and operating line. Okay, so for these two, you need to plot them first, and then you can, after you plot them, you can plot your stages that you need to plot. So we start with equilibrium line and then operating line. So for equilibrium line, I have an equation, as I already mentioned. So for equilibrium line, I have equation y is Henry constant divided by pressure times x. Henry constant is given 876. Pressure is given 10, and what you need to do, just put them together, and by this you can have the relation between y and x. Once you do that, you have pressure and Henry constant, pressure 10, Henry constant is given. So once you have this, you have to plot the equilibrium line. To plot the equilibrium line, you need to give several x, like what I have done here, and then you have to calculate y. So you choose some x, let's say from x0 to some x. So there is a limit actually here, but you cannot go below 0, but you can go a little bit upper than, like this. So I will tell you why we choose this value. You will see in the next slide there are some reason that we use this value. So you give several x. For each x, you put it in this equation. This is a column that you create by yourself. You just select some values, random values. So each values you put it here, and you find your y. Okay, and you calculate your y from this equation and just sort all together. But this is lowercase x and lowercase y. What we need capital X and capital Y. Capital X is x divided by 1 minus x. capital Y is Y divided by 1 minus Y. Okay, so you need these two parameters. Alright, so what you can do, you can still use the same table. For each x, put x in this equation and find the capital X. And for each y, just put it in this equation and find the capital Y. And then you can convert the lowercase x and y to capital X and Y. So you will use the same numbers, you put it in this equation and just calculate the corresponding capital X and corresponding capital Y. Okay, and you create this table and then you have to plot. Sorry, this is not the correct one. X and Y. So then you need to plot your Y versus X. This is what you need to do. This will give you the equilibrium line. So I'm gonna do it, I'm gonna go to the next slide. So this is how you will plot your equilibrium line. Let's say for X, for the first point, for this point, X is how much? 0, 0, 0, 1, Y is 0, 0, 8, 7, 6. So I choose these 2 points. I choose this X, put it in this equation and find the capital X, which is pretty much the same. That's why when as I told you, when X is very small, X capital and X star are almost the same. And for Y, I need to do the same. I need to do the same. So I just use this Y in this equation and I can find the capital Y. I did it for this point. I can continue for the other points and complete this table, and then I will plot Y versus X. So this is the first step that we need to do. Next, what we need to do, we need to find our X and Y in other points. Okay, so just eliminate this, this is not correct. So what we have here, we have our we have, okay, as I said at the beginning, we have our gas which has how much CO2? It has 10% CO2. We want to separate 92%. What we will have at the end, we have only 8% that will remain at the end. So the mole fraction of my CO2 at the end is how much? Actually, this is again, this is the lowercase n y, okay, lowercase. So at the end, how much I have at the end, which is at the top, which is y1, is 8% of initial mole fraction. 8% of initial mole fraction. That gives you how much? 0.00008. Okay, this is the mole fraction of CO2 at the top. So you can use equation, you know, the equation that you have, the relation between y, lowercase y and capital Y, to convert this to the capital ones. And okay, so we can also calculate the amount of CO2, because we know the mole fraction of CO2 and we have the amount of the gas, which is 1 mole per hour. So we can also calculate the amount of CO2 at the beginning and at the end. The amount of the carrier gas, the mixture gas, doesn't change from beginning to the top, from bottom to the top. It doesn't change. So we can also use this equation and find the amount of CO2 at the bottom and at the top. So okay, you can, again, as I said, the definition, okay, we know that 10% is in the gas at the beginning. 10% of is CO2, 90% is nitrogen. We have 1 mole per hour, 90% nitrogen, so we know that we have 0.9 mole per hour nitrogen. So by knowing this, we can also calculate the capital Y by using this equation. We know that capital Y is the mole of CO2 divided by mole of carrier gas. So the mole of CO2 is 0.1 divided mole of carrier gas, which is 0.9. So we can put this in this equation and find the capital Y. We can do the same thing for capital Y at the top of the column that we have Y1. Again, we have nitrogen. Nitrogen doesn't transfer, so the amount from beginning to the top is the same. From at the beginning we had this much CO2, at the top we have this much. So it gives me this value. This is one way to calculate it. Another way is just use this equation. Yn plus 1 is y divided by 1 minus y. Yn plus 1 n plus 1. So here you have 0.1, 1 minus 0.1, that is 0.1 divided by 0.9. That gives you exactly this value, 0.011. For y1 capital, you can also use this equation, lowercase y, 1 minus lowercase y. That will give you exactly the same value, 0.0089. So this is another method that you can find. So you find, and now you have x0 at the top, which is pure. You have y1 at the top. You have yn plus 1 at the bottom, but you don't have xn. We don't have xn. We have all these three, but we don't have this. So how we have to calculate this? We have to use the balance to find xn, and then we can plot our operating line. So how we find xn? How we find xn is okay. It's very easy. First of all, it's very easy. Like we know. First of all, we have to find the. We have to plot the minimum minimum slope operating line, L over G minimum. So by using that line, we can find xn related to the minimum operating line. After that, okay, once we plot the minimum operating line, we can find xn related to the minimum. By using that, we can find this slope, and this slope times 1.5 gives us the real operating line. So once we have the real operating line, the operating line, the real condition, which is 1.5 times this one. So then we can find our xn. So how we do this? I prefer to show this on a graph in the next slide. So we have one point at the bottom of operating line, which is top condition, pure solvent and gas that is leaving, and we have also yn plus 1 at the bottom of the column, or top of the operating line. So this is my equilibrium line that I use the data in the tables. We have several data in the tables. We just plot those data, y versus x. We can have this line, equilibrium line. This is my equilibrium line. So for the bottom, for the operating line, I have one point here. X is 0, y is this. This is related to x0 and y1. This is one point. Another point that I have is at the bottom of the absorber. I know that my yn plus 1 is this value, is 0.11. So the minimum operating line is the operating line that will have an intercept with equilibrium line. So it means my yn plus 1 and xn will be on equilibrium line. This is my xn, yn plus 1 and xn, which is all the time on operating line. In the minimum slope, it will be on equilibrium line. So I need to go, I have this y, I need to go read this xn. That if you read this xn, you will get it this value. That is your xn that you will read it from here, is from this value, which is 0.00105. So now you have 2 points. This is one point, this is another point. So you have 2 points. You can find the L over G minimum, the slope of this line. The slope of this line, which is L over G minimum, how we find it is, let's say this is your point A, this is your point B. So when you have 2 points, the slope of the line between that 2 points is y. Is yb minus ya divided by xb is xb minus xa. So if you do so what is your yb is here 0.11 minus ya is here 0.0089, xb is here 0.0005, xa is here 0, which is the 0 value. So if you calculate this, it should give you something about 96.2. So that's the slope of minimum operating line. You will find in this way. So you have one point, the another point will be on the equilibrium line. Which point? The point that cross this y. So you just plot the horizontal line, just cross it, and then you remark this point and go read the x related to that point. So this is the slope of the minimum operating line. Okay, so this has to be corrected. If you calculate that value, it gives you 96.2. Please correct it in your slides. The real operating line is L over G. The real one is 1.5 times L over G, which gives you this value. So now again, to find the stage, you need to go plot your real operating line. This is your real operating line. Just let me clean this a bit here. I'm just cleaning this figure here. So now again, I have my point here, okay, and I have a slope. New slope is this slope. So I have one point and a slope. I can plot the line. So you know that your line, your second point has always this y. This is the y that you always have it, and This is the y that you always have. So in case of minimum slope, you go read this x here, this x. Now that you have another slope, you have another x. This is your new x. So how we find it? So you know that you have 1 point and you have the slope. You can plot this line. If it's hard for you, you can go find this point directly. How you can find it? So based on the equation that I already wrote here for you, let's go to the next slide. I can show it to you here. So we can use again the same equation. The slope of the line between these 2 points is the difference in the y of the 2 points divided by the difference of the x of that 2 points. So the slope, we have it, the new slope that we calculated, 145.8. The y1 and yn plus 1, we know it. y1 is here, yn plus 1 is here. We have it, both of them we have it, we just put it there. x0 we know, which is 0, is here. The only unknown will be xn, or this x here. This is the x that we need to calculate. So if you put all this equation here, you can find xn 0.0007. So now you have this point and this point here. You just connect these 2 points to each other. That gives you your operating line. Just connect it to each other. So this is your final operating line that you have in this question. Now you have to start plot the stairs that I will show you in the next slide. So okay, this is what we just found, xn, the final x. So that if you plot the stairs, it gives you 4 stages. Let me show you how you plot the stairs. So you have all your points that you need. This is your initial point. This is your another point to terminate point. So this is your operating line. Let me plot it in another color. So I just plotted in blue. So you have, this is your operating line here. This is your operating line. So you can start from bottom or from top, doesn't matter. Both of them give you the same result. So I will start from top, from here. This will be mentioned to you, start from top or bottom. So this is my first stage. Then I go to the equilibrium. So I come from operating line to equilibrium, then from equilibrium to operating, then operating equilibrium, equilibrium operating. I will continue like this until I reach to my final point. Okay, so I just plot horizontal and vertical line between operating and equilibrium line. Then I will have to count the number of stages. So this is one equilibrium stage because it's on equilibrium line, right? Second equilibrium stage, third, and fourth. How many stages I have? 1, 2, 3, 4. Totally, the number of stages that I have is I have 4 stages. Okay, so that's all about plotting, finding the number of stages. So the next topic in this unit is sizing the pack column. Sizing means finding the diameter and the height. So I'm just gonna stop here in this video. I'm gonna continue this part in another video. So